All right. Hello. And welcome to the chapter review section of the 341 online course. So, what I've decided to do, I've made some notes and I will post those. I'm going to break these videos up into one chapter at a time kind of thing. Hopefully, they'll be a little shorter than the lecture length videos and a little more digestible, therefore. Okay. All right. So, let's start from Chapter 1 then. Okay. Chapter 1. So I guess this is basically on sets and functions. Okay. And as I've said at the top of the review notes here, I mean, this is all meant to be kind of an outline, okay? So this is not a list of worked out problems. This is me just going over basically a list of topics that we've covered that you should consider yourselves responsible for. Let's see. Nice cold black coffee. All right. Let's see. So, all right. Let's start with basic notation. Of course, you should know what these things mean. X belongs to A. X does not belong to A. A is a subset of B, or alternatively, A contains B. It's a superset of B. You should be familiar with the idea of set notation, so you should be able to tell me what a set is by saying that it's the set of all x such that x satisfies some property, or properties, I should say, probably. Okay, so you could, for instance, insist that x be less than or equal to 5 and strictly greater than 1, that kind of thing. Alright, so that basic set notation you are responsible for. Do not, under any circumstances, drink or inject or ingest bleach or other disinfectants. Nor should you miraculously find a way to do it, inject UV light into your veins. Okay? I've tried to stay quiet about this, but this is enough. The man's an idiot. Okay? Just please listen to the doctors. Alright. This notation, n, that's the natural numbers. That does not include 0. Okay, just for the record, that became a bit of an issue in one of the questions on the midterm, right? Just the question of whether or not 0 was part of the natural numbers. Some people forgot that it was not, and therefore their answer was almost right, but not quite right. R, of course, is the reals. Z, that's the integers. Did you see? What are the? Never tell me the odds. That piece of chalk just fell off the top of the chalkboard and right in between my fingers on this blessed day. Integers and then rationals. Okay, so those are the major sort of special notations for subsets of the reals that we've had. Set operations. Right, so you should know what these things mean. Again, really it would be, be like basically rebooting the entire course to write out all the definitions for these, okay? So I'm just telling you what you need to know. If you don't know it offhand, then you should go look it up. But the union, right? Something belongs to either A or B. The intersection, whose members belong to both A and B. Also the set A without B, meaning those members of A which are not also members of B. Okay? And then we have infinite unions and intersections. Right? So then we have the union from n equals 1 to infinity of an. Here I will bother to remind you. This union is the set of all x such that x belongs to some an. Okay? N equals 1 to infinity a sub n. So the intersection from n equals 1 to infinity of the a sub n's is the set of all x such that x belongs to all a sub n's. Okay? Right. Then we have the following basic definition. A function f from a to b is a rule that assigns to each x in A and f of x in B. Well, I should say A, this is important, a unique f of x in B. Okay? Sends things in A to things in B, and for each thing in A, it sends it to one and only one thing in B. So here then A is the domain. B is the codomain. And f of A, so this set is the set of all elements of B such that y equals f of x for some x, right? So that set is called the image of f, or sometimes the range of f. The image of f And finally, if, say, C is contained in B, then F inverse of C is the set of all X in A such that F of X winds up inside C. And this is known as the pre-image. Pre-image of C. The pre-image of C. Okay. Right. So that's some basic terminology and notation. Let's see what else. All right. So important properties that functions can have that you need to know. So let's suppose that f is a function from a to b. F is injective if f at x1 is not equal to f at x2 whenever x1 is not equal to x2. In other words, f is injective if it sends distinct points to distinct points. Okay, so for instance, the function f of x equals x is definitely injective, sends different points to different points, whereas f of x equals x squared is definitely not injective, right? It sends both 1 and minus 1 to the same point, namely 1. Okay? All right. No, I didn't suffer any catastrophic injury. I just, my garage now contains about the biggest homemade climbing wall that you could possibly fit in there. So this video here just represents a break in the real function of my pandemic home life, which is getting better at climbing. Okay, so now F is surjective if for all y in B there exists an x in A such that f of x is equal to y. In other words, for anything in the codomain, it's f of something. Something from the domain hits that under f. Okay? And then I will just briefly say that injective plus surjective, this is the same thing as what is called bijective. Bijective. So, for the test, you should definitely be able, I can ask questions, I probably will ask a short answer question that says something like, give me an example of a function which is injective but not surjective, or surjective but not injective, between these two sets, A and B. And as we saw from the midterm, it's actually really, really important that you pay attention to what A and B are, okay? So what happened on the midterm was that I asked you for a function which was surjective but not injective, but it had to go from the I believe the integers to the natural numbers, right? So the easiest answer was absolute value of x plus 1. What a lot of people did was just demonstrate, a function, say, from an element, a set with two elements, a and b, to a set with one element. They just said, well, I'll take both points in the domain, I'll send them to the same spot in the codomain, and that function is surjective, and it's not injective, and yes, you're right, it's neither of those things. What it isn't, however, is a function from the integers to the natural numbers, which are the domain and codomain that I specified, okay? So don't get lost completely in just making sure that your function satisfies whichever one of these qualities I ask for. Also make sure that your function, in addition to satisfying the qualities I might ask for from among injectivity, surjectivity, and bijectivity, also satisfies that it goes between the right two sets, right? It's the right domain and codomain. Okay. Right. Oh, forgot one thing. Right. So, if f from a to b is bijective, then there exists an inverse function f inverse from b to a, defined by f inverse of f of x is just equal to x. That's how you define it. Why is that good enough? Why does that define f inverse? Well, for starters, since f is a bijection, what is that dust bunny doing? Oh my God, there's nasty. Yuck. Gross. Just won't go away. There. Okay, so since f is a bijection, it is in particular a surjection, meaning that every single thing in B has the form f of x. Meaning that I'm not missing the definition of f inverse here for anything. Every single thing in B looks like this for some x. In fact, every single thing in B looks like that for some x for some unique x. That is, I can make this definition, and this is what is called well-defined, because once I know what f of x is, there is absolutely no ambiguity about what little x had to be, right? And that's from the injectivity. There's only one place that f of x could have come from, and that's this x. Okay, so that defines it. That's the inverse function. Alrighty. So that was section 1.1, section 1.2. This is on mathematical induction. And there is, of course, a high likelihood that there will be some kind of mathematical induction question on the final, both because you're responsible for it and because I didn't ask one on the midterm. So it would make a pretty good question. I'm not guaranteeing anything, but, something to think about. So, the first thing from this section is to recall, and this is something you should know, the so-called well-ordering property of n. Which says that if S is a subset of the natural numbers and S is not empty, then S has a least element. And that's it. A non-empty set of natural numbers has the smallest element to it. Okay? So, for instance, if I said, consider all the people on Earth that have at least one hair on their head. Consider the set of all natural numbers represented by the number of hairs on those people's heads. Does that have a least element? Yes, it does. I mean, if you look up on your own head and there's at least one hair there, then the set of people with at least one hair on their head is non-empty. Right? The set of numbers of hairs on those heads is non-empty. And it's a set of natural numbers. Therefore, it has a least element. Okay? So no matter how weird the way in which you come up with a set of natural numbers is, as long as you can guarantee that it's not empty, then it will have a least element. Okay. From that, one gets the principle of mathematical induction. Oh, so induction. Let S be a subset of the natural numbers, and let it satisfy the following two properties. One belongs to S, and two, if K belongs to S, then K plus 1 belongs to S. Then S is equal to the natural numbers. That's it. That's the entirety of the induction principle. I am not going to go over a bunch of examples of induction, okay? I leave that to you. The purpose of the review here, like I said, is to make sure that I hit the high points in terms of what you are responsible for. This section of the textbook has a ton of examples that you can work out in the questions and the exercises. There are zillions more online that you can find that are not only posed but also worked out, okay? I'm not going to ask you the world's hardest induction question. I'm not going to ask you the world's easiest one, but, it's not going to be, like proving Fermat's last theorem or something, okay? The main thing is that you have some familiarity with the mechanism and you're reasonably able to carry out a few algebraic steps to carry out the inductive step. Right. So that is pretty much the entirety of section 1.2. That's what you really need to know. This and the well-ordering principle. Okay? Okay, and then we're on to section 1.3, which is finite and infinite sets. Okay. So let's just go through the definitions. S is finite if it is either empty, so for convenience we'll call the empty set finite, or there exists a bijection f from S to some initial segment of the natural numbers 1 through n for some n. Okay? And of course, as it turns out, because that's a bijection, the n for which this works, if it's a non-empty set, is unique. Right? The number of elements in the set is a unique number. Right. So I guess you can. Right. I forgot. You guys get. I keep on stopping, thinking to myself, I better give him time to write this down. But I don't have to. You can just pause the video and rewind if you want. So I'm just going to blaze ahead here. Reminds me of my freshman chemistry class. We had this guy whose name I can't even remember as an instructor because all the students just called him Turbo Prof. And this guy, 2 overhead projectors, and he's just going between them like every 30 seconds. A new slide would come up on one or the other. It was impossible to follow. No phones, no pictures, no nothing. I just, you had to like literally limber up from your writing hand before you went in there. Okay. So S is infinite if it is not finite. Right. S is countable if it is either finite or there exists a bijection f from S to the natural numbers. Okay? Otherwise, right. S is uncountable. And I'll revert to our shorthand notation there. Uncountable. And then I will remind you of this little result that demonstrates the importance of knowing what the contrapositive is in mathematics, in life generally. You never know when it'll come in handy. Right? So, theorem. So we have 2 sets, S subset of T. So 1, T finite implies that S is finite. And then S infinite implies that t is infinite. But in fact, 1 and 2 are logically equivalent statements, right? So part 2 is the contrapositive of part 1 and vice versa, right? The contrapositive is this logical idea that, the statement, if it's raining, then the ground is wet, is equivalent to if the ground is not wet, it is not raining. A implies B is the same as not B implies not A. Okay? Oh, here's an important theorem. Let's see. The following are equivalent. So here are some characterizations of countability. Okay, so 1, S is countable. 2, let's see. There exists a surjection F from N to S and 3, there exists an injection. Well, let's give it a different name, G, from S to N. Right, so this says somehow if there's a surjection from the naturals to S, then somehow the naturals are bigger than S, which means that S has to be countable. If there's an injection from S to N, it means that S fits inside N, and again, it makes sense then that should mean that S is countable. Okay, so these are 3 equivalent statements, and they could come in handy because I could very easily ask you, is the following set countable or not? In fact, I did ask that on the midterm, and I might ask something like that again. Okay? All right. So, as examples, recall then, this is important, that the rationals are countable. And another important example that we covered is that if a(n) is countable, then the union from n equals 1 to infinity of all the a(n)s is also countable. Okay? So those are 2 basic examples of countability. And then the final important thing from this section, and therefore this chapter, and therefore this particular chunk of the review video series, is Cantor's theorem. Which says the following: if A is a set and P of A is equal to the set of all B such that B is contained in A, right? That's the so-called power set of A, the set of all subsets of A. There is no surjection phi from A to the power set of A. Okay? So that's an important theorem to know. All right, so that concludes the review of Chapter 1, and I will be back at some point later with Chapter 2. Bye-bye.